Welcome to the third and final presentation in Unit 2. It says to err is human. It says to err is human and to blame it on a computer is even more so by Robert Orban. Okay, so the student should be able to understand the conceptual development of and using physical models. Students should be able to calculate values to compare how closely models adhere to an experimentally determined scenario. So what you should already know. You should already know that all empirical laws are based on empirical evidence. Empirical evidence can be used to predict untested values. In fact, that's the whole reason by deriving these equations. And that interpolation or extrapolation of untested data can be highly inaccurate depending on the circumstances. Okay, so physical models can be used to explain behavior within a system. Models that can be applied to multiple systems become physical laws. The only reason why you have a physical law is because it works everywhere. It works in this system, it works in this system, it works in this system, it works in all systems. So that's the reason why you have physical laws. Now, models and physical laws are subject to change. And this is one of the things that people have the most problems with, is this idea that models can change. Our understanding of the universe is the best we have based on the available information. Okay, a great example of this is Newton's law of universal gravitation, okay, commonly known as n-log. Okay, n-log, or Newton's law of universal gravitation, was changed to fit Einstein's theory of relativity. And it was done when there were new observations, the fact that light, whenever it goes by a sufficiently heavy object, will actually curve instead of going straight. Newton's law of universal gravitation had no explanation for why this would work, but relativity did. Now, as an interesting side note, that doesn't mean that Newton's law of universal gravitation was wrong. It wasn't. It worked for the systems that it was being applied to, but it didn't work for all of them. Relativity takes the best parts of Newton's law of universal gravitation and then expands it. So, for example, here is the universe. Okay? Here are the systems in which Newton's law of universal gravitation works. And if you look, something on the order of 90%. Here are the systems that we now have where relativity works, which relativity and Newton's law of universal gravitation together make up about 99% of the systems. There still are 1% of the systems that we can't account for with those two theories. That doesn't mean they're wrong, it means it works for what we have. So we come to big idea number 3. The world around you can be explained using simplified models. So, system. We've already described this. A system is any portion of the universe that's being studied. As the system is whatever the experimenter wants it to be, and laws are applicable to all of them. So, a scientific model is designed to make the world easier to understand. Okay, you are trying to understand, define, quantify, predict, simulate, and visualize. With the key thing, the ultimate goal is being able to predict. Once you can predict, that shows that you truly have an understanding of what's going on in the scenario. So models are used whenever you have direct measurement under controlled conditions, and it's really unlikely to be able to develop a lot of these. Like, for example, if I'm looking at a star system and I want to know how galaxies are formed, it's really hard for me to make direct measurements under controlled conditions. I can't manipulate a galaxy formation in order to see what's actually happening. So the motion of a ball down a ramp has many uncontrolled variables. Okay, you have air currents, you have friction, you have how somebody's releasing the ball, you have imperfections in the floor. There's a lot of uncontrolled variables. So as a result, interpolation and extrapolation do not always match what we experimentally do. Okay, in fact, they vary from the prediction, indicate that our model is flawed. So the fact that we have some discrepancy between the predicted value and our actual values that we test indicate that there is going to be some variation, that it's not a completely accurate model. And physics models will fail. Okay, Hooke's law, which is something that we'll talk about a little bit later this year, talks about the idea that you have a spring, and whenever you stretch that spring out, it requires more force, and that it's a linear relationship. In other words, the more force you put on it, the more this spring is going to stretch out. Well, it turns out that Hooke's law only works for a very specific region. At that point, once you exceed that region, it becomes a little bit more of a complicated problem. In other words, the model for Hooke's law only works for the set of conditions. In fact, a lot of times the physics models will fail, but they're once again they're not wrong. They only work for the specific circumstances in which we're looking at. Now, it's really important that you test a model. Like we said, scientists are always continually testing models. Okay, once again, Isaac Newton's model of gravity was infallible for centuries. Einstein tested it under extreme circumstances, with the key being extreme circumstances. Okay, things like black holes, in order to find the flaws. So Newton wasn't wrong. In fact, if you look at Einstein's relativity, whenever you put it under the conditions that Newton had, it reduces down to what Newton said, but it's just slightly other factors that weren't accounted for. Now, whenever we're looking testing to see whether a model is correct or incorrect, you want to look at it in terms of percent error. So all models will have an acceptable degree of error. It depends on what model you're looking at, what your instruments are. There's a lot of factors that go on to determining what is an acceptable percent error. Okay, but percent error can be used to test the model's prediction. You have the theoretical value, which is what the model tells you. It's your prediction. It's the book value. Okay, and then finally, you have the experimental value. In theory, you'd get a 0% error for a good model, but that's just not likely. You should always have some built in error just because of the limitations of your measurement tools. Well, one of the ways that you can test error again is standard deviation. So, standard deviation is how far a value is away from its normal. Now, the assumption is you have a normal population, and a normal population is there is some sort of average value. Okay, and there's a normal distribution, which is what this is. It's sometimes called the bell curve, a normal distribution that goes out from there. So IQ is an example of a normal average value. So the set value for an IQ as an average is 100. Okay, and it goes down and it goes up from there. You have very, very, very few people that score way out here on an IQ test. You have very, very, very few people who score way down here on an IQ test. And that's because it's a normal population. And so you can tell the difference between measurements based on standard deviation. So it says the accepted model for gravity predicts that a basketball will fall at 4.9 meters in 1 second. It says a student testing the model measures the ball to fall 4.6 meters. It says what is the percent error? So the model is our 4.9 number. That's our theoretical value that we should get. The measurement is 4.6. And then finally we divide it by 4.9. We take the absolute value, which is what those lines are, and we multiply it by 100 to turn it into a percentage. Whenever you do that, you get 6.12%, okay, which is a pretty reasonable model. Okay, now once you've established this percent error, the next step is to try and explain why you have a 6% error and then try and fix it from there. So for example, one of the things could be how the ball was released. Maybe the person, instead of just dropping it, kind of tossed it up a little bit to get their hand out of the way, and then it fell. And that could be an explanation for why it didn't, fall as far in 1 second. Another explanation could be that the timer didn't time it correctly, so that you have an error for what is actually 1 second. The person jumped the gun. Another one is the fact that there's air in the way. And was there some sort of air resistance that pushed the ball and made it not go as far? So the next thing is to try and establish what factors you can improve to make the model better. Okay, assess the accuracy of the Beer-Lambert model between absorption and concentration and justify your response. So this right here is the model. The Beer-Lambert response assumes that you would have a 100%, it goes up like this. Okay, when in actuality it does this kind of logarithmic one. Okay, now assess the accuracy of the model. Well, the model is highly, highly accurate in this region right here. Okay, as long as you have an absorbance value that small, this is where Beer's law works really, really, really well. But it does not work very well on the extremes. So whenever you're using the Beer-Lambert law, you need to make sure that you're using it only for small values. And finally, it says calculate the standard deviation for the ACT science test given the scores below. Okay, so now whenever you calculate the standard deviation formula is S, which is our standard deviation, is equal to, and then you have these fancy terms right here. Okay, and we're going to talk about what these mean in just a second. Okay, n represents the number of data points that you have. So for example, I have 5 data points. 5 data points. Now in my formula, it's n minus 1. So on the bottom here, I'm going to have 4. And we have the square root. Okay, now the next thing we have to do is you would go ahead and say um, x with a bar over it. X with a bar over it represents the average. So whenever you take all these and you add them up and you divide by 5, you get the average number, which I got was 25.8. So that's the middle score right here, 25.8. So x bar is going to be our average. Now x is going to be every individual data point. And then this right here means the sum of. So in order to find x minus x bar, you have to take your value, 22. You need to subtract 25.8, which is the average. Okay, and then it says to square it. And then it says to do that for all the data points, not just 22, but 36 minus 25.8 plus 28 minus 25.8. And you need to do that for all 5 data points. Once you do it for all 5 data points, then you take that and you divide it by 4, and then you have to take the square root at the very, very end. Okay, and it becomes really important that you actually do that. Now, whenever you do this, you should get a number like plus or minus 4.5. And what that means is that the standard deviation for this thing is 4.5. So the average value is going to be 25.8 plus 4.5 or minus 4.5. So if you are average, if you scored between, let's say, 21.3 and 30.3, that's where almost everybody is going to be. Okay, now if you were one standard deviation higher, okay, you'd have to score 30.3 plus 4.5. So you scored between a 30.3 and a 34.8. Now these are all normed tests. These ACT science, the SAT, all those tests that you're going to take are going to be normed tests, which means it has to follow this pattern that we talk about, a normal distribution. So in order to be in the top whatever percentage of the SAT test, you have to score a specific value, and you will get some practice with working with these standard deviation values in your interactive practice.